Hello everybody and welcome to my talk on the conic advantage in mixed integer nonlinear programming. If you pick up a classic textbook on optimization, you'll most likely find the definition of two problem classes, linear programming and nonlinear programming. These are in some sense the extremes, ranging from the most simple to the most general. It's therefore no surprise that conic optimization is a problem class in between. What may surprise you, however, is that Lagrangian duality theory, known and loved in linear optimization, can be used to derive conic optimization as the natural extension of results. This explains the many nice dual properties found in conic optimization. For this slide, I prepared a special surprise for you, namely that best practices in mixed integer nonlinear programming actually leads to conic optimization. Let's see if you agree. So to start off, we'll use this standard model where we minimize a nonlinear objective function subject to a number of nonlinear constraints and integrality on a subset of variables. The first migration comes from a set of prominent people in the field, namely to migrate to a linear objective function. So in my example, I have x2 squared in the objective, and as you can see, I can easily move that into the constraint set. The purpose of doing so is to avoid interior solutions which cannot be separated by cuts. To reflect this in our standard model, we're going to change the general function f of x to ctx. The second recommendation is to distinguish convexity to avoid unnecessary spatial branching and really just make everything easier for yourself and the solver. To reflect this in the standard model, we're going to split the constraint set into two, the non-convex constraints and the convex constraints. The third recommendation is to preferably implement your model using built-in atoms rather than relying on callback functions. This makes it much easier to debug the solver as you don't need the user code in order to reproduce a bug. You also get rid of callback overhead, which can be quite significant given that you have to ask for every single property of these constraints. But finally, and probably the most important property, is that users don't have to fear ill-defined boundary points. They can use logarithms without fearing its evaluation near zero, and they can use norms without fearing being asked to evaluate the gradient near zero. Rather, they would just be using built-in atoms of the solver. For instance, the hypograph of the logarithm or the epigraph of the 2 norm. It would then be the responsibility of the solver to ensure numeric stabilities of these atoms and generally specialize for high performance. The only disadvantage to this recommendation is that you are now then limited to a predefined set of atoms. I'll return to this point later in the talk. So to reflect this in the standard model, we're going to separate the linear part of the constraint set, which will operate over the full set of variables in this case, and then nonlinear constraints which will operate on a subset of variables, a selected subset. This explains my notation here. And we know that these atoms here that we have, they should be numerically stable, they should distinguish convexity, and they should be versatile, so they can be used to cover a wide range of applications. But I'm thinking of a fourth property that would be really useful here. Can you guess what I'm thinking of? Perspective transformation. This is really essential when you want to provide a stronger model formulation. So Cereus-Zeraris characterized the closed convex hull of the union of convex sets using this perspective transformation. And let me just be clear, if you have integer variables, you have unions of convex sets, and you may need the perspective transformation. This may be useful to you. If you're interested in this part, I recommend you look into Günlich and Linderoth, who used it to tighten a bunch of commonly appearing sets, and generally recommended as a useful tool. Going into the details, if you want to support the perspective transformation, you need the variant of the atom which is homogeneous, that is, in which all variables are scaled by a non-negative factor. Let me take the examples from previous. In case of the hypergraph of the logarithm, we would be scaling each variable by a perspective variable s, and if we rearrange this, we can recognize it as an exponential cone. If we do it to the epigraph of the 2 norm, we would see that the scaling factor would actually cancel out. It would not be introduced. And we can recommend this is already homogeneous, and we can recognize this set as a quadratic cone. But did you notice the abuse of notation here? Yeah, you probably did, because it's not well defined to divide by 0. So rather than writing the functional form here for a scaling factor greater than or equal to 0, I'm going to write it for a scaling factor greater than 0. This is well defined. Then I'm going to put it in a set and take the closure of it so the set becomes defined for s equals to 0. This is the proper way of writing it, and since it's a set, we can give it an appropriate name, which we can use in our standard formulation. So rather than writing the functional form here, we're going to change to a set membership notation, which really just represents the exact same thing. And now our journey is complete. This is a mixed integer general conic optimization model, and all we needed to do was migrate to a linear objective function, distinguish convexity, implement your model using built-in atoms, and implement solvers to support the perspective transformation, all of which gave us a computational advantage. And now you can enjoy the power of Lagrangian duality theory for the convex subset of your problem. If you're interested in mixed integer conic optimization, I compiled a list of resources here to get you started. I recommend you pause the video and look if there's anything interesting here, because the rest of the talk I'm going to spend on the one disadvantage that we identified, namely that you're limited to a predefined set of atoms. So the important questions here is what cones to support and how to decompose nonlinear constraints into conic atoms. To address the first question, we already know that it should be numerically stable, distinguish convexity, and versatile. We also mentioned that the atoms should support perspective transformation, but this is trivially satisfied now that we're dealing with cones. So where to begin from these 3 properties? If you start with a clean slate, where would you look first? One idea could be to look for convex cones with a low degree of nonlinearity, maybe even quadratic-like, so Newton-type methods are expected to solve the relaxations faster. If you like this idea, you're going to love the seminal work by Nesterov and Todd. They coined a property called self-scaled, which does exactly what we wanted to achieve. Self-scaled cones achieve the best-known global convergence rate among Newton-type methods. And better yet, we don't need to look for cones that are self-scaled anymore because they have all been characterized as the set of symmetric cones. In MOSAIC, we support all real-value symmetric cones. In the case of the nonlinear ones, I've listed here, it's the quadratic cone, which can be used to represent the 2 norm, the epigraph of the 2 norm, and the rotated quadratic cone, which is basically just an orthogonal transformation of the quadratic cone, which has a notational convenience. And finally, there's the semi-definite matrix cone. At MOSAIC, we also implemented 2 non-symmetric cones after a lot of effort. And with this effort, the non-symmetric cones, are now comparable in performance to the quadratic cone, or at least almost. This is the exponential cone, which can be used to represent exponentials and logarithms, and the power cone, which is a generalization of the rotated quadratic cone to simple powers. One observation that we made over the years is that almost all convex optimization problems appearing in practice can be formulated using those 5 cones. And we are not alone in this observation. You can look into this paper, for instance, where they show that all convex instances in the MI NLP Lib 2.0 are all representable using these cones. In general, the observation is that if you do the reformulation, you'll get a boost in solving time, so everything solves a bit faster due to the computational advantage we mentioned earlier. And in this paper, they even show that previously unsolved instances can now be solved with this reformulation. I think that's great. So to address the second question on how to decompose the nonlinear constraints, I recommend this MOSAIC modeling cookbook. And although the name suggests that this is tightly related to MOSAIC, it's not at all. It can be seen as a regular textbook on conic modeling without any references to MOSAIC commands or the MOSAIC API functions. It includes lots of examples, tips and tricks, and resources and references to other resources on the subject. In this talk, I'm going to give you an examples which I picked up over the years that users struggled with. I will try to do it in a slightly more mechanical way as to inspire research in automating this process, or at least part of this process. So if you're faced with the hypograph of this expression, you can use numeric methods, for instance, a graphing method here, to see that we should be able to represent it for x less than or equal to 1. If we look into the expression graph for this, we would see it as a product of two independent operands, each of which would have a subtree in the expression graph. And it's therefore natural to try and start to see if we can represent these operands independent of each other. Unfortunately, that is not possible using convex cones. In particular, the Hessian matrix of this product is indefinite everywhere. And this means that the hypograph of it or the epigraph of it is going to be a non-convex set. This also tells us that in order to represent this hypograph, the relationship between the two operands is going to be very important for our success. So let's look into that. y2 can easily be written as a function of y1. And this gives an expression for y1 as a function of y2. And by multiplying both sides of the equation by y2, we now obtain a new representation of the product. Simply substituting back in the definition of y2, we get a conic reformulation. In particular, we have two terms, each of which can be recognized using the modeling cookbook. First of which is a rotated quadratic cone, and second of which is a power cone. The second example is going to be very similar, so feel free to pause the video at any moment and give it a try for yourself. Using the numeric method to verify convexity, we see that we should be able to represent it for x greater than or equal to -1. If we try to see it as a division of two independent operands, we're going to fail exactly as before, for the exact same reason. So the relationship is important. We can write y2 as a function of y1, or we can write y1 as a function of y2. And doing the latter, we can divide both sides of the equation by y2 and obtain a new representation of the division. Inserting the definition of y2, we get a conic representation. In this case, we have two terms, one of which is a constant, and the other of which can be looked up in the modeling cookbook. In this case, it's a rotated quadratic cone. For the next examples, it's going to be a bit harder, and we're going to be needing a sine sum of squares decomposition. Allow me to explain. For any real symmetric matrix, in this case Q, you can put it on diagonal form, for instance using eigenvalue decomposition. For this particular decomposition, however, I'm going to assume that D is a signature matrix. That is, all the diagonal entries are plus or minus 1. This is simply a matter of scaling and filtering out eigenvectors associated with the eigenvalue 0. For your convenience, I included Julia code to automate this step. The result is that for any vector A in the column span of G, you can find column weights A tilde to generate this vector A and rewrite the general quadratic form on the left to the sine sum of squares on the right. you see that the sine sum of squares involves a variable u, which is basically just an affine expression in terms of x. So the first part here is a sine sum of squares of affine expressions in x, and this is a constant, which can also be written as plus minus a constant squared. So we are done. To try it on an example, I'll use this set, and you'll notice that the expression on the left is indefinite everywhere. So if we wanted to do the hypograph of it or the epigraph of it, we would not be able to because it would be a non-convex set. But in this case, we only need a sub-level set. And if we use our numeric methods, in this case graphing, you'll see that it's basically just a union of two convex sets. And those convex sets we should be able to represent those independently of each other. So using the eigenvalue-based sine sum of squares decomposition, we can reformulate the original constraint into the sine sum of squares using 3 squares. But this decomposition is not unique, and if you look further, you can actually also find one in 4 squares, which is much more elegant. Well, in either case, you are very close to a conic reformulation, and the only thing stopping you is the sign of this expression. If this is either non-negative or non-positive, we can reformulate the inequality using a quadratic cone. Otherwise, you have a disjunction, and you can branch on it to do the reformulation in each child node. Now, to have a bit more experience using this decomposition, I'll give you one more example. And in this case, we should be able to represent it for x1 and x2 greater than or equal to 0. The eigenvalue-based decomposition can be used to rewrite the denominator in terms of 3 squares, and simply by rearranging this, we can get something that is very close to a quadratic cone. The only thing stopping us is this expression over here. If only we could substitute it with something squared. Well, using a power cone, we can. And doing so, we can reformulate the original constraint and represent the inequality using 2 cones, the power cone and the quadratic cone. So in summary, conic optimization is like a sweet spot in nonlinear optimization. You can derive it from linear programming if you try to extend results of duality theory. And you can derive it from mixed integer nonlinear programming if you try to avoid the computational disadvantages following the best practices mentioned. With conic optimization, you have no issues with smoothness or differentiabilities, and models can be solved efficiently. In particular, we saw that symmetric cones achieve the best known global convergence rate among Newton-type methods. For further information, please recall the list of references I have had for mixed integer conic optimization, have a look at the Mosaic Modeling Cookbook, the Mosaic Optimization Suite, and look into our applied optimization tutorials. Thank you very much, and have a great day.